Welcome back, Raiders. I am just full of aura today. Before we jump in, does anybody have any questions for me related to math?
What's in front of 5?
What's in front of 5 or what's behind 5? What comes after 5 maybe is
What comes after 5, Mr. Holloway?
6, 7. All right, gross. So, welcome in, everybody. Today, we are skipping the review chapter. And the reason that I do that, I do it intentionally. Even if we go over the review chapter now, in 6 weeks when we see that stuff again, we'll need another small review, so we may as well just embed that in the course as we go. So right off the bat, my formatting with stuff. Today we will begin chapter 1. And in chapter 1, we have, I suppose I should have a book somewhere. Don't know the name of this chapter. My guess is limits, but we'll see what it comes out to. In chapter 1, we are going to be looking at limits and continuity. So those two, limits and continuity, is our focus throughout chapter 1. Limits and continuity. You will never see me write continuity again. That's probably a lie, but I will try to avoid it. In parentheses, here's the shorthand that I will use for continuity, continuous. I use CONT, and I just stop it. Cool. All right, now specifically in chapter 1, we will begin with chapter 1, section 1. So I format this as 1.1, and then I used to do 1.1.1 if it was day 1, but we'll just call it 1.1, and we'll just ride with it until we're done with it. And then we'll call it 1.2. So we are looking at limits of functions. And we'll zoom in. There will probably be another section named the same, but limits of functions right off the bat. Okay, so cool. As we go through here, our first main topic is we want to be able to make sure we can think about what limits are actually asking, right? There's going to be a lot of new notation. The concept isn't really new, though. So our main topic to begin with is we're going to talk about the slope of a tangent line, of tangent, and henceforth you will likely see me write tan unless it's in a formal definition. Slope of a tangent line. Okay, now if you want these additional resources, I'm going to sketch graphs up here. I'm not using graph paper. Up on the table here, I am putting some sticky notes with graph paper. If you want one, you're welcome to come grab one, like a sheet at a time. I don't think we need it for this because we don't need real specific, but it's entirely up to you. Okay, as we look at it, we're going to sketch you a little graph real quick, and we're going to go in quadrant 1. So we'll use this to kind of start thinking about it. And because you might be rusty with your math, what should I name this axis? Okay, sounds reasonable. How about this one? I could call it y, and it would be correct to call it y, but more commonly f of x is what you'll see, but I'll call it y because that's what we're used to. And I'm going to draw some curvy function passing through here, and I have a couple questions that aren't directly related to limits, but it's good to review. So let's say I have something that's doing something like this. 2 questions, one of them related to this. Is anybody in here colorblind? Okay, because if you are and I'm using green and red and all that, you're going to struggle. All right, what should I name this function? I wouldn't call it x. The variable, it'd be of x, but what do you want to call it? I don't really care. F seems reasonable. Let's call this f of x. Here it is, and it's awesome. Now, arbitrarily, I don't have to have numbers or anything like that. What I want to do, though, is I want to put a point along the x-axis. We'll call it right here. We'll name that C. And then we'll go some distance further, and I don't know what we call it. We'll find a different point elsewhere. But if I wanted to identify this point, could we name it? Can you tell me what that ordered pair is? You don't give me numbers, but you should be able to give me something. Ooh, close. I heard X, but I don't like X necessarily. I'm at C right here, right? So this ordered pair, to me, if we write it, it has C. And what about the Y value of it? One more time. Don't care if you're wrong. I just didn't hear you. So it could be, it doesn't look like 0 here. It could be, and maybe I'm just bad at drawing. But without giving a number, what function did we just plot that on? F, right? And we did at which point? C. So let's do f of c. Everybody cool with just that little part right there? I'm going to put one more point on this, and maybe just for clarity, I'll put a capital P so we can name it P, just so we can talk about it. Okay, I'm going to pick a different x value somewhere, and we're just going to make it arbitrary. I'll do it right here, and we'll say, hey, that one is just x. And I don't like that color purple. It's not very dark. Okay, here's x. Could I put the same point or a different point, but could I do the same thing on the function right here? Write me that ordered pair as well. Nosy, love it. Bea, if you want to check with the neighbors, yours is good. Super close. I see one little issue with it. Love it. You plugged in X, right? And I can tell you did. And you got F of what? Should it be? Good. Love it. Cool. I see everybody's whose I checked just now came up with the point X comma something. F of x. Okay, double check your letters. If you have f of c or some other value, I think that conceptually you're probably okay. You just have the wrong letter. Now, I have 2 points on this lovely curve of f, right? Could I draw a single line between them? Any 2 points you could draw a line through, right? Like that's what the definition of a line is. So as we look at this, I don't want you to draw yours yet, but I'm going to draw it up here so we can think about it. We have, that color's going to be hard to see. I could draw this line. Now, what I've just drawn is a line that crosses through 2 specific points of my function. This is not a tangent line. We can dig way back to geometry. I don't know if we'll be able to remember this. Somebody already said it. Louder, Angel. Slope. So it does have a slope. It is another S word. A line that touches this twice is not a tangent yet. It's a secant line. So let's start right in. A little bit of algebra review. From this image, I want to know, and I'll call this point Q just so we can refer to it nicely. What I want you guys to do, or us to do rather, is from this picture, can we find, or let's find, what letter do we normally use for slope? M? And if I want to specify that it's a slope of segment or line PQ, you could be really wordy with it. I'm going to use my subscript. I want to find the slope of this. Well, the good news, I guess it's only good news. The first part of good news is that we've dealt with slope in 7, 8, 9, 10, 11, 12 grade, or at least 11, I imagine. But, gosh, you know, it's August 21st, I'm rusty, I just don't remember what slope is. I'm going to call on a random person in 15 seconds. I need somebody to help me find the slope. And if you don't know, I'd use the next 15 seconds to chat. 15 seconds, random person. Slope. Give me the wordy version of slope. It's something over something. Rise over run. Is rise going in the y direction or the x direction? Y. So we have a change in y first. And Kalisha, I loved everything that I heard except you were a little bit backward, I think. Okay, so let's find the slope of this line real quick. If we start plugging and chugging, here we go. Does the order matter for the numerator? I'd say that there's a best order to take, but whichever one you pick for the numerator doesn't matter as long as your denominator matches afterward. Delilah, how do you want me to write the change in y that we see here?
y2 minus y1.
Okay, what about with these points specifically? F of x minus f of c. Those are the 2 y values that we have on our graph, our ordered pairs, all divided by what? Anybody and everybody. Okay, why can I not do this? We need to be consistent. The first number you put in the numerator doesn't matter, but once you decide what goes first, you have to follow that same convention for the denominator. Okay, that would give me the slope of the tangent line, right? Or sorry, the secant line. Now, the big idea with calculus and where this is going is we want to know what happens when we get really close to something. Arbitrarily close. Did I say when we get to it? No, I don't care about what happens when we get to it. I only care about what happens as we get how close? Infinitely close. The real word is infinitesimally, but I'm cool with infinitely close or arbitrarily close. As close as you possibly want. Because however close you decide to start, I can get closer. And we just say that, okay, so for however close you want to get. Now, as we look at this, this touches this twice, right? Okay, you're not going to change this on your notes, but I do want to make sure that we can see it. If I instead had put point Q here, do we still get a secant line? How many times does it touch at those points? 2. What if I move closer? Because I'm getting arbitrarily close is literally what I'm doing right now. Do we still have a secant line? Eventually, those points are going to be so close together that they're essentially the same point, right? There's no distance between them. When I get so close, I would then have a line that looks like this. I wouldn't even be able to distinguish that there's 2 points here. Do I have a secant line anymore? If they're arbitrarily close and it really exists as a single location, I'm only touching it at 1 point now because they get so close together that they're just 1 point. It's not a secant if it doesn't touch twice. What do we just change into? This is changed into a tangent line. This is the motivation behind how we're going to calculate any tangent line. We found the slope of a secant line. Turns out it's the exact same method that we use to get the slope of a tangent line, but we have to let x and c get really, really close together. Arbitrarily close is going to be the language that shows up all the time. Okay, if you are looking at this and going, oh, I don't really know yet, don't stress. This is day 1. We can change a secant line to a tangent line by moving one of those points really close to the other. Feel okay? Feel absolutely awful. Thumbs up says, all right, I don't get it entirely, but I'm okay with the concept. Thumbs down says, what the hell is going on? Where am I? And anywhere in between. You don't have to broadcast it to everybody, but like especially if you're this person, I really need to know that. Okay, cool. So what we have here is a natural transition. We are going to let, when we do our calculus, x and c get really close together. Now I'm going to change that language. If I could physically grab point Q right here, and I could drag it, could I make x approach c and get really close? Like I just drew that picture of that happening, but if I could drag it, I could literally see it happening, right? As c approaches x, or as x approaches c rather. And I could see that happening. What we have just worked out with the fact that we can think of that point moving and getting closer to x or c in this situation, we have introduced our big idea for the first 6 to 10 weeks of class. Our first big idea that we're going to see for the very first time is the idea of a limit. Idea, and this is not a definition. I started with all caps because of how important this is. There are only 3 main topics in all of calculus. This is the first, the limit. Cool. So, right off the bat, we're going to give it the really informal version, and we'll clean it up and we'll get better notation as we go. So, here we go. The idea of a limit, just to start with. We want to know, what does the y value, which you're going to see some of my shorthand. If I just write y val, huge stretch, what do you think val is short for? Boom, value. What does the y value of a function, and again, we're going to get func. What does the y value of a function approach, which can somebody give me another way to say the word approach? Get close to. Love it. So the limit, most basic. What does the y value of some function approach or get close to as x gets, and I'm going to be real, I'm going to put this in quotations because this is such an important part, arbitrarily close to a value, and I'm going to call it c. It's pretty common to use that. A value c. Okay, this is it. Now, when we look at these, there are 3 ways that we can approach this mathematics. We can approach this mathematics analytically, which is going to be what I prefer. That's doing the algebra to really figure out what's happening here. We can approach these graphically, which is pretty nice and easy as well. Or we can approach it tabularly using a table, which is pretty nice and easy also, but it's tedious if you have to type it into a calculator and such. Quick check. We're not going to be using these calculators this year. We have better ones. Does everybody in here know how to use this calculator? Bits and pieces of it. Those of you that weren't here last year, Leanne, have you used TI-84s before? Okay. Have you, Aisha? All right. So check it out. I didn't even check. Let's go see how many of those batteries, like go grab a calculator. Don't care what number you pick. Doesn't have to be your number. If batteries are dead, I'm going to have you just share with your neighbor, whoever's closest. Before you sit down, I check to make sure it turns on. Sad why? The latteries are bad? I mean, you can switch those B and B, but you never know. Share with the neighbor for now. Okay. All right. I'll make you guys change these at some point this week. But here we go. This is kind of new. We probably talked about this briefly last year, but we're about to do our very first true problem that would be only within the realm of calculus. So let's do it. You're going to be, you would want to say calculist, but that's not what it's called. Analysts are people that do calculus. Algebrists are people that do algebra, but it's fancier algebra. What do you call somebody who does geometry for a living? A geometer. Like those words are actually real. So here we go. We're going to see the notation in our first example. So what I want us to do is make sense of this. Making sense is what I'm going to name this example. If you want to name it something else, you can name it my first limit. You can make a scrapbook this weekend, all of that. Making sense. All right. So we're going to see new notation. Let's check it out. We're going to use our calculators, and I'll model that up here on the board as well. But for our first example, and I'll wait till everybody's caught up because the notation is really important, and I'm crazy about it, so we're going to be important. Okay, here we go. We are going to take the limit as x approaches something. The way that this is written, and wait until I have the whole thing done before you write it. We are taking the limit as x approaches 1 in this example of something. Now, the function that we're going to be dealing with, f of x, it's our argument for this, the same language that we use, the argument of a sine function, of a log, whatever. Whatever we're taking the limit of, I'm going to refer to as the argument. I want us to use our calculators to make sense of the limit as x approaches 1 of, in the numerator, we get x squared minus 1, and we're going to divide this bad boy by x minus 1. Now, you have no idea how to do this on your calculator. Not yet. And maybe you do, but we'll get there. Here's what I want us to think of. As I'm looking at this, I'm wondering, this function f of x, that is that x squared minus 1 thing, over x minus 1. I want to know, as I pick x values, how close to 1? Arbitrarily close. What happens to the values of my function? Now, there's a natural approach that one might take. If I want to know what does the function get close to at 1, anybody have a gut feeling for the thing you might try first? What's up? So 0.9 is a great thought. I don't, like, if that's your first thought, love it. But if we want to, like if I said f of x is 2x, what does it get close to as we get close to 5? Anybody just naturally want to plug it in? Like, can we just plug in 1 here? We can try. Let's see. If we plug in 1, we get 1 squared, 1, minus 1, the numerator is 0, right? And now I have to divide that by what? Uh-oh. Can't do it. Dividing by 0 is undefined. So our function breaks here. And I can see that because we can't even get a number out of it. But I don't need to know what happens at 1, only how close? Arbitrarily. Now here's a really important distinction. I don't want you to see the graph because I want us to do this analytically first. But check it out. Don't draw this, but if I have a number line and I put 1 on it, and this is the only number that I have, 1. I want you to get close to 1. Give me an example of a number close to 1. 1.5, give me closer. 1.01, 1.0001, and I can just keep adding zeros and get closer, right? You've gotten closer. If we pick 1.5 or whatever those numbers are, 1.01, I'm just going to say 1.0001. Maybe this is 1.1. It's not really to scale. Is that the only side that you can get close to 1 from? So just now, if we were approaching and we're picking these values, are we going toward 1 from the right or from the left on a number line? This is from the right. If I want to know what happens as I get close to it from the right, I should probably also ask what question? What happens as we get closer to the left? So here's what I'm going to do with these calculators specifically. If you have one that works, awesome. If you have one that did not turn on just now, share with a neighbor. But let's dig into this particular problem right here. So we have our lovely function. I don't want you to see all the answers. We have our lovely function that we're going to type in. So I have in the top left, y equals. Okay, your calculators only understand as much as you tell them. We don't always put it, but fractions, big ratio things like we have is that x squared minus 1 thing, they have parentheses around the numerator and denominator. In the numerator, using parentheses, I'm going to choose x, which is this button right next to the alpha key. And what was that actual function? X what? So x squared, here's my square button right next to kitty corner or a diagonal from 7. So I have x squared and minus 1. That was my numerator. And I'm going to divide this bad boy by another set of parentheses. What was our denominator? X minus 1. Okay. I have this in. I'm going to hit enter. It is now saved in my calculator as y1. Okay. We're going to do one little thing on this calculator starting tomorrow. I'll give you guys the 84s. I changed my mind during the course of class. Like I should just start teaching on those right away. But we'll get the 89s tomorrow. Now, if we go back to our home screen though. How many of you could ask your calculator to find me y1 of a number without me showing you again how to do it? Anybody know how to make this function say f of, but it's y1 instead? Y is a variable, right? Is there a variable option on your calculator? Vars anywhere? Okay, so if we hit vars, how do I get to the y stuff that we just typed in? There's a tab up here, right? We have vars and y vars. I'm going to hit 1 to the right. You are cool to interrupt me. Anybody who's near Leanne or Aisha, if you guys will help as we're doing this, or if you need help as we're doing this, use each other's resources. Okay, y vars. I want to evaluate a function, right? Okay, and where did we just store that? Is it y2, 5, 9, 1, 1? Here we are. So I'm going to kick back over to my other screen. We're going to try to divvy up this labor real quick. First thing I want to do is get close to it from the right side. Okay, so from the right, looking, I'm going to have your guys' attention. Let's see, 1.1 is a pretty close start. Okay, Rafa, I want you on your calculator to do y1 of, you're going to do 1.1. Okay, this row, Riley and Makisha and Leanne, I'll come and check with you too. You're doing 1.01. 001, 1.0001, 1.00001. So above it, hit enter. And then in parentheses, you're doing, so this is understanding it's f of 4 zeros. 1 point, let's do 3 zeros, 0, 0, 0, 1. And then close your parentheses. Okay. All right. And Leanne, I'll come check with you because we're going to do the other side as well. So we had several numbers. We are just going to combine all of our ability together. I'm going to make a table. And I want to know what happens as x gets close to 1. Just now, did we approach it from the right or from the left? From the right. So right in the middle of my table, I'm going to put 1 because I already tried this and it didn't work. At 1, it was undefined. Like there was just nothing there, right? It was a hole. It was dividing by 0, not allowed. So we have to do this backward, and we might not put all 5, but I want to make sure we can do it. The closest group that I had, arbitrarily close, they had 1/10,000th, I think. Might have been 100,000th. I don't remember. You had 1.000. 2.01? Okay, when you typed this in, what did you get? F of that. Somebody second that. Angel, did you get the same thing? Okay, so I have the same one on mine. I just want to test it as well. 2.000001. Okay, I'm going to record this value. Now, I'm not going to make us write all of these because they're awful, and I'm just going to double check. I had 4 zeros. 0, 0, 0, 1. Okay. Angel, I'll come take a look and we'll see why the error happened. Okay. Let's skip a row, although I think Bea and Aisha probably have it. Delilah, Sean, or Kalisha, you had 1.001? What did you get?
2.001.
Huh. All right, and Rafa, 1.1, what did you have? 2.1. Okay. From only 3 points, as we look at this, as I get closer to a value of 1, which means I'm coming from the right here, I was at 2.1, I was at 2.001, and now I'm here. What would you say as I get arbitrarily close to plugging in a true 1, the y values get arbitrarily close to? It looks like 2, right? I agree with that. So I'm going to make just 2 little additions here. I'm going to have an arrow, or just I'll indicate here from the right. And I'm going to put positive because that indicates that we're coming from numbers that are larger or more positive. Okay, it seems to approach 2, and I can see that happening. On the flip side of stuff, if we want to come from the left, we're going to do the same numbers. I want everybody to go ahead and calculate 1 or 2 of these, and I'll come around and check. Give me some numbers to the left of 1 that are equally and arbitrarily as close. 0 is really far away. 1.9 would be this one, right? Because it's a tenth away. 0 is to the left. You're not wrong, Sean. I just want to be a little bit closer. If I pick 1.9 here, what could my next one be? 1.99, like that's closer. I'm going to use the same convention, 3 decimals, 3 decimals. And this last one would be 1.99999, right? We're approaching, it would be 0, thank you. Anybody see that same mistake and notice that I was doing it? Something to the left of 1 is not 1.9. I was just stuck on my 1. 0.9 is really close, it's a tenth away. 0.999 is really close. And you already have it saved in your calculator. Find me these 3 values. Yep, so I'm just, I hit a second, so if you hit the blue key, it'll be the blue one. And then I'm going to retry this. Don't stress with the calculator. We're going to use it for a day. I'm not crazy worried about it. I just reset your calculator because my guess is somebody had a weird setting. I set and quit to get back on home screen. And then we'll do y1 of. So let's try that. We did 1.0001. There was a setting wrong in your calculator. Nothing needs to be different. So with these, and we'll see it on the other ones, if I want to do the same thing, I can either go back and be here to sit back, or if I just want to redo it, I hit second and enter. I can just change this number. So now I'll do 0.00009. I'll delete that one, and let's just see what we get. Cool. It should be 0.9999999. I was rough. I stuck on the point zeros because, and this is just me, 0.999. I did it wrong. Okay, so let's check it at 0.9. What do you guys come up with? 1.9. Okay. How about at 0.9999? Huh. How about at this one? It's probably the same thing, right? 1 point, but just more 9s. This one, we are coming from not the right any longer, but from the left. If positive means we're approaching it from the right side, from a more positive number, what do you think we're going to use to say from the left? A negative. Okay, so as we look at this, and we'll look at the graph here in a second, and it'll become super obvious. As I look at this, from the right side, what y value do I approach? 2. From the left side, what y value do I approach? So check it out. We're about to write our first calculus solution. If you want to rewrite it, you can. I'm just going to copy and paste. What do you think we're going to say that the limit of this function right here is as x gets arbitrarily close to 1? It is 2. Now, this problem is super tedious when you have to do it numerically. It is not fun to do problems numerically for me personally. If you really like using your calculator, these might be awesome. Let's take a look at a couple more, because I don't think that we really truly have to use our calculators like crazy here. Okay, so I'm going to hop on Desmos real quick, and let's take a look at that graph. Desmos. All right, so we had y equals, it was x squared minus 1 over x minus 1, right? Before I type it, anybody know what shape this is going to be? It's a straight line. Now, there happens to be a hole at x equals 1 because it would divide out. If you remember simplifying all those big ugly ones last year, you can't even see the hole because it's arbitrarily small, but if I zoom in and I try to calculate what it is, it's undefined. We can't do it. Graphically, this question is so simple to look at, and I'm just going to make us do one without having to write anything, but check it out. As I want to get closer to x equals 1, which is what I'm doing right here, I'm getting closer and closer, do the y values indeed get closer and closer to 2? As I come from the other side, from the left, as I get closer and closer, do my y values get closer and closer to 2? Look at that. You could determine the value of a limit just from a graph. In fact, let's do a crazy one right from a graph. Okay, we will see this one. You don't have to write this down. This graph will show up again. Sine x over x is an interesting function. It's special. You need special tools to even figure this one out. We'll learn those tools. It's called the squeeze theorem or the sandwich theorem is what we'll cover eventually. But right now, 60 seconds, I want you to determine for this function, sine x over x, what is the limit as x approaches 0? I want you to not only have an answer, but to be able to justify it, because I'm going to ask some follow-up questions. As x approaches 0, this function approaches what? 60 seconds, you need an argument, talk with your neighbors. If you don't understand the question, I'm here to clarify. Yep, as x gets closer to 0. So as you pick a point and you start dragging towards 0 from either side, what y values does your function get really close to? I don't think we'll need a full minute. We might need like 5 seconds. Gut feeling. 1. Let's check that. Now, you don't have the ability to like physically drag a point in front of you, but I do. From the right or left first? Sure. Here we go. 3 is not very close, or pi isn't very close, but we can get closer. Here I go, getting closer and closer. You guys claimed it gets closer to 1. Hey, is it getting closer and closer to 1? What's going to happen when I get to 1? Or 0, I'm sorry. It's going to be undefined again, because you can't divide by 0. As I get closer and closer from the left, what do the y values get closer and closer to? Was it the same from both sides? Holy cow, you guys are doing calculus. Super hard, right? Cool. All right, so for today, I want you guys to practice a little bit with this. You're in class right now. As you're practicing with stuff, you're going to interrupt whenever you need to ask me questions about things. I'm going to check all your TI-89s, and I'm going to start giving you guys your TI-89s. Okay, you may not use them today. Again, if you don't want to take one home, you don't have to. You should. Don't leave them in your cars. They're a $150 calculator. Cool. We will learn to use them. It's pretty much, keep it for now, because if the batteries are dead. But in case, because you guys don't get to, like, I'm not going to let you take your phones to take pictures of it here and now. But what I will do is I will borrow a student book, and I'm going to give you guys the first assignment. And my homework will be due tomorrow at the start of class. Yep, welcome in. Okay, so notationally, the way that I do this, and I'll try to be consistent with this, but this is the first homework from section 1.1. So here we go, homework. And I'm going to do it on the Google Classroom, and then I'll put a picture of it on the video as well, but I need somebody's textbook. So let me go to calculus here. And then as soon as I'm done recording, I will save the video. I'll post the video to YouTube. Thank you very much, and I'll give this right back to you. So let's check it out. Very first homework assignment, I guess second because syllabus, but that's not due yet. Here we go. It is 8:21. Homework 1.1. You will find waiting lovingly for you on page 86. I think.
Wasn't there like a certain way you wanted us to do?
Yep, and we'll talk about it. Okay, on page 86, I want you guys to do problems 7, 9, 11, and 17 through 28.
Oh, I love it. Love it.
Okay, here's the homework, and I'll go back to using this. This is 1.1, basic limits is what we just did in class today. There's our homework assignment, and I will post the YouTube link. I'll actually put it right where it is, but I'll do it here in a few minutes. Okay, for homework stuff, remember the wheel will decide, but tomorrow's a Friday, so I'm definitely taking it so I can get one in the grade book. Very specific format. What I would like you guys to do for your homework, and I'll put this back up in a second, while you're writing it. If you didn't do it today, that's okay. We'll make sure we have it in the future. I want you guys to do your homework like this. If this is a page, so here's your homework, like the sheet that I assume you're writing on right now. I would say, here's my name, Ballaway. Look at that. Okay. I don't care if you say it's calc or not. I'm going to be able to look at your page and see that it's calculus. As long as it has homework 1.1 along with the assignment that I just wrote down in the top left corner, I'm good with it. Okay. Reminder on homework. We're in an AP Calc class. Your schedules probably vary pretty wildly between each of you. Some of you are taking a lot of really rigorous courses, I would guess. Some of you not as much. Last year, I told you to never sit at home crying in your bed at 2 a.m. because you're doing math. How long should this assignment take you? So last year, I think I put the cap at like 35 or 40 minutes. I said never spend any more time than this. This year, we're going to say 45. Okay, I don't think this will, I think you'll come close to getting a big portion of it done right now, to be honest. 5 minutes. Okay, 45 minutes is your deadline or your hard time limit at home. If a homework takes you more than 45 minutes to do, it means that I didn't do a great job teaching it or we have little gaps. Let's fix that. Cool.
Okay.
45 minutes, you stop wherever you're at. Honestly, cool. All right. And real quickly, I will post this on the video. I'm sorry, I stole that from you. Okay, here's our problems, right? 7, 9, 11. If you, I keep just totally psyching you out. I'm sorry about that. Okay. If you don't want to take your book home on the YouTube video, here's number 7. Here's 9. 11. I don't remember the other numbers. 17 through something. And 17 through 20 is right here on the YouTube video, so you don't have to take your book. And here are these other ones. Read the directions. The homework is there for you, and I'll post the video. I'll start getting you guys some TI-89s. You can use the yellow calculators for today. You're very welcome.